Our final speaker is Dr. Sam Ting. He is the Thomas Dudley Cabot Professor of Physics at MIT. Throughout his career, he's led international collaborations in experimental physics using accelerators in the US, Germany, and Switzerland, and on the Space Shuttle, and now the ISS. His contributions, too numerous to mention, include the discovery of nuclear antimatter, measuring the size of the electron family, discovery of the gluon, which is the particle responsible for transmitting the nuclear force, and discovery of a new kind of matter, the J particle, for which he was awarded the Nobel Prize. He currently leads a 16-nation collaboration on the Alpha Magnetic Spectrometer, an instrument on ISS that searches for the existence of antimatter, the origin of dark matter, and properties of cosmic rays. And we've given Dr. Ting a little bit more time, and we're happy to welcome him.
So where is the pointer?
So I think the bottom button.
So let me share with all of you the latest result of the AMS experiment on the International Space Station. How do I advance this? Oh. Yes. So I want to remind all of you, Senator Hutchinson was responsible in 2005 for designating the US portion of the International Space Station as a national laboratory. And in doing so, confirmed the important role of science on ISS and US leadership. You have heard the brilliant talks by my predecessors. This laboratory, which its capability to support many kinds of scientific research, including complex modern accelerator type experiment, is a unique facility. So to honor this remarkable legislation, I would like to report to you the progress of a modern accelerator type experiment in space. The unique potential for US ISS laboratory to conduct fundamental science research is easily recognized. Remember, to study cosmos, you need to detect the signal carrier. There are two kinds of signal carrier. Those without charge, neutral cosmic rays, light rays and neutrinos. And they have been measured for many, many years. And then there are particles who carry charge. Because they carry charge, it must have a mass. And because it has a mass, it's absorbing Earth's atmosphere. So to study its fundamental property, you must go to space. So this is an experiment studied neutral cosmic ray, neutrinos. And this experiment is quite interesting. It's located in South Pole. It's 1.4 kilometers under the ice, 1 cubic kilometer in dimension. Inside, there are 5,000 detectors, and this is their control room. Cosmos is the ultimate laboratory. The highest energy particles are produced in the cosmos. What is shown here is the largest accelerator, has a circumference of 16 miles. It produces particles of 7 trillion electron volts. But cosmic rays of 100 million trillion electron volts has been detected. So that means no matter how large accelerator you build, you cannot compete with space. That's a very important concept. So the highest energy particle has been detected with a very large detector. They used, there's no way to come back. Yes, thank you. So cosmic rays, primary cosmic ray, go to Earth's atmosphere and produce secondary cosmic ray. So you measure the energy of the secondary cosmic ray, you get the primary cosmic ray. So there is an experiment in Argentina, and so this is the size of the city of Paris, so 10 times the city of Paris, and to measure the highest energy cosmic rays. AMS is a US NASA Department of Energy-led international collaboration, and with strong support from William Gerstmaier, the leadership of Johnson Space Center, Space Station Management, and also the NASA AMS Project Office, Kim Borwick and his team. So we have a lot of people, and one of my little job is to make sure when I'm not around, people agree with each other. Doesn't happen too often. So this is the detector. Took many years to build. It has 300,000 channel electronics and 600 microprocessors. It's 5 meter by 4 meter by 3 meter. It weighs 7.5 tons. So it's a particle physics detector normally used in accelerator, except now in space. So its capability is to measure trillion electron volt particles very precisely. All the particles and nuclei are defined by their charge. Charge means their location on the periodic table, their energy, or rigidity. Rigidity means momentum per unit charge. So on top is a transition radiation detector, identify electron positrons, 9 layers of silicon detector, measure charge and rigidity, a calorimeter, measure energy of electron positron, 2 banks of time-of-flight counter, measure charge and energy, a magnet, measure the sign of the charge and rigidity, a ring image Cherenkov counter, measure charge and energy. Therefore, charge and energy are measured independently by many detectors. So in 6 years, we have collected more than 100 billion cosmic rays, up to multi-trillion electron volt. This is more than all the cosmic rays collected in the last century worldwide. But that's nothing. Important thing is the precision of the detector now can decode what is the origin of cosmic rays. So the first issue let me share with you is dark matter. And remember your high school physics. And so you have a galaxy, and you have a star rotating around the galaxy in a closed orbit. A closed orbit means gravitational force and centrifugal force are balanced. Otherwise, you will not have a closed orbit. From this, you measure the velocity is equal to gravitational constant and times the mass within this region divided by r. For this galaxy, you will see the velocity goes up because you have more mass, and then out of the luminous region, the velocity continuous goes up. The fact that it continuous goes up means they are material you cannot see. And this is true for the 1,000 galaxies we observed so far. Therefore, the existence of dark matter is not a question. The question is, what is dark matter? Now, collision of cosmic rays in space produce energy. Energy produce positrons and antiprotons. Collision of dark matter, you don't know what it is, but as long as it is a particle, it will produce energy. Energy will produce positrons, antiprotons, and deuterons. And so this excess from above the ordinary cosmic ray collision is what we're looking for. So these are the very simple theoretical model to search for the origin of dark matter by measuring positons. Collision of dark matter produce positons which will increase with the energy, then become flat, goes up, and then sharply drop down. The sharp drop down is because of finite mass dark matter cannot produce infinite energy positons. So this is just a conservation of energy, but this is a unique signature that you have from particle collision. And this will be production from ordinary cosmic rays. So this is our latest result based on 6 years and 1.58 million positons. So these are our data, and this is the theory. They seem to be in reasonably good agreement. Of course, the error in here is still quite large, and therefore you need to go to 2024 or beyond to reduce zero. So far, this is the only experiment show we understand dark matter. But to pin it down, we need to continue to do experiment until 2024 or beyond to see the sharp drop-off. But recently, in New York Times, there was an article about the experiment done by Department of Energy on high-altitude water Cherenkov gamma ray detector, measure positons. And this experiment says their measurement shows all results measured by MS cannot come from other cosmic ray sources such as pulsars, and therefore most likely it is from dark matter. This is a very important independent verification announced in Science of last year. And this is the result of our antiproton to proton ratio, and this ratio shows our measurement also agree with dark matter model and cannot be explained by collision of ordinary cosmic rays. Another topic we just started is to look for antideutrons. Antideutrons from dark matter annihilation are abundant at low energies compared to antideutrons from collision of ordinary cosmic rays. In 6 years on the space station, we have collected 100 billion protons. Think about it, 100 billion is a big number. And we have 100 million deuterons. So this provides a unique opportunity to look for cosmic antideutron. Namely, the data already exists. Now we need an enormous amount of computing time to process this. This is our current measurement. Only a few days ago, it shows our spec of a proton, of a deuteron, proton, K plus, pi minus, K minus. These are particles with a lifetime of a billionth of a second. They come from a particle interact with the top of the detector and produce the secondary particles. But the detector is so sensitive, it can pick out particles live only billionths of a second. So it's a super precise detector. And this is if you look at antiproton, it's supposed to go down to zero, and this axis is the signal of antideutrons. And so soon there will be an important announcement how large is the antideutrons. Let me now share with you the issue of elementary particle in space. When you break the atoms apart, there are hundreds of different kinds of elementary particles, muons, pions, kaons, but only 4 of them, electron, proton, positron, antiproton, have infinite lifetime. So they live in the cosmos forever, and they are detected by AMS. Protons and antiprotons have mass 2,000 times the mass of the electron positron. Because they are so massive, they lose energy much less in galactic magnetic field than electron positrons. So the smaller the mass, the faster you lose the energy. So protons are the most abundant cosmic ray. Before AMS, there has been many measurements of proton spectrum by balloons and by satellites. And this measurement, for example, in this energy, somebody measures says it's 8, the other measure says it's 14. So the difference about a factor 2. With such a large error, the first consequence is you make the theorists very happy. They can every theory will fit the data. This is our result from AMS, based on 300 million protons. And this result shows the measurement is to an accuracy about 1%, agrees with traditional model up to this energy. Above this energy, there are unexpected excess. Namely, the traditional model is incorrect. So a theory cannot be proved by an experiment, and the theory is incorrect. A very interesting consequence is the measurement of proton spectra as function of energy, shown in this axis, as well as antiproton spectra, shown in this axis. And their momentum spectra is identical. But this is not too surprise, because proton and antiproton have the same mass. What is unexpected is electron, positron have identical mass, but their spectrum is very different. It's very difficult to understand. It's totally different from the ground. Proton and antiproton are the same, you can imagine, because they're the same mass. Electron, positron, they're the same, but they behave very differently as function of energy in space. And this is based on 23 million electrons, 1.6 million positrons. And so it's not due to statistical effect. Another very strange thing is antiproton spectrum in red, proton spectrum in blue, and positron spectrum in green have the same energy dependence or momentum dependence. But positron has a mass 2,000 times smaller than proton, antiproton. And they should have been very different, but they are not. And recently, we published 2 very important papers on cosmic rays. Traditionally, there are 2 prominent classes of charged cosmic rays. One is called primary, another is called secondary. Primary cosmic rays, such as proton, helium, carbon, oxygen, are produced at their sources and travel through space without interaction with other cosmic rays and are directly measured by AMS. So they carry information on their sources and history of their travel. Before AMS, there are many measurements of primary cosmic rays because they are very abundant, and particularly on helium, carbon, oxygen, and you can see they're vastly different from each other, and you have no way to see what is going on. This is the AMS measurement. When we measure this, we see helium, 90 million events, carbon, 8.4 million events, and oxygen, 7 million events. Enormous amount of events, but the energy dependence is exactly the same. The three are totally different elements in periodic table, but the energy dependence is really unthinkable why they behave exactly the same and first goes down and then goes up. And then there are secondary cosmic rays, lithium, beryllium, boron. They are produced from collision of primary cosmic rays. And so primary cosmic rays collide with each other, then produce secondary cosmic ray detected by AMS. So they carry information about the history of travel of both primary cosmic ray and secondary cosmic ray, and the property of what is the interstellar medium. So this is before AMS, measurement of lithium spectra. The error is very big, and so you cannot make anything out of it. This is the AMS measurement of lithium spectra based on 2 million events. First, it disagrees with the theory. This is a theoretical prediction, and also disagree with previous measurements. A very important thing is if you look the lithium spectra, the pink one, or the red one, and the green one, boron spectrum, where the absolute value is slightly different, the shape is exactly the same. There's absolutely no reason in space they behave like this. No theory predicts this. Then if you look at lithium and beryllium, and you look carefully, lithium energy, the rate of yield of lithium is exactly rate of yield of lithium on this axis is exactly the twice of beryllium. The different exactly by factor 2. No theory predicts that. Also, above certain energy, they again is exactly the same. So this is our understanding of all the cosmic rays. Primary cosmic ray, lithium, beryllium, boron, have identical energy dependence from each other, and they are different. The secondary cosmic rays have identical energy dependence from each other, but they're different from primary cosmic ray. So cosmic ray then, on the periodic table, can be divided into two classes, and they have exactly the same energy dependence. Nobody ever dreamed of that. So for all the cosmic rays in space then, you have primary cosmic ray, you have particles like proton, positron, antiprotons. You have secondary cosmic ray, you have electron. So in space, all the particles can be classified into 4 classes, only 4 classes. So now let me share with you something totally unexpected on the question of antimatter. Antimatter was first proposed by Paul Dirac, who received the Nobel Prize in 1933. In his Nobel lecture, he stated the equation of motion on relativity, on quantum mechanics, always has m a square. M is mass. So it's m times m or minus m times minus m. So most of people say this is a fictitious, threw it away. But Paul Dirac asked, what is minus m? And lead to the theory of antimatter. Antimatter was discovered by Carl Anderson, and this is the first positively charged electron. So antimatter does exist. The question is cosmic antimatter in a complex form. The Big Bang origin of the universe required matter and antimatter to be equally abundant at the very hot beginning, because before the Big Bang, nothing exists. So at the beginning, there must be equal amount of matter and antimatter. Cosmic antimatter in complex form, such as antihelium, has never been observed. One of the main physics research topics in the last half a century is to search for explanation, the absence of antimatter. Antimatter will not exist if symmetry is breaking, if symmetry doesn't exist. So there's a very large accelerator, 60 miles in circumference in Geneva, and there are experiments called Atlas. There's an experiment in Japan. It's a huge experiment, and this is filled with water, and there's two guys in a boat. When the water goes up, they can get out and look for lifetime of protons. So despite the outstanding experimental effort over the last half a century, no symmetry breaking has ever been found. Therefore, the observation of a single antihelium in cosmic ray is of great importance. So we today have observed few events with charge not +2, but -2, namely negative, and with a mass around helium-3 and helium-4. And this is one of the events in the bending plane, perpendicular to bending plane, and projection measures the velocity. And this is momentum, its mass is helium-4, and its charge -2. On the periodic table, helium on Earth is +2. -2 means it's negative matter. The rate is quite low, 1 event in 120 million. 1 in 120 million, if you think about it, it's a very small number. And this is the reason you have not seen it in newspapers. And so we're still collecting events, hopefully within a short time, and we will try to announce this. So AMS is the only magnetic spectrometer in space. The results contradict previous measurements and theoretical models. The surprising results from AMS are opening a new chapter in the understanding of cosmos. And I do want to thank Senator Hutchinson and also the management of JSC and Space Station to make this experiment possible. Thank you.
Okay, I'm always kind of blown away when I hear Dr. Ting talk, but I would like to see if we have any questions. I know you're just all kind of absorbing all this fun changes to our understanding of fundamental physics. Well, we are going into a break now, so feel free to come up to Dr. Ting. I hope he'll have a few minutes to interact with folks if you do have questions. Mm-hmm. And I believe, are you coming up? Good, to tell the next event. I did want to thank all our speakers for your fascinating presentations.